Hello, friends, welcome. Today we will start with the next unit. It is the synchronous motor drives. So, to start with, we will try to brush our basics about synchronous motor and then we look at the control aspects. So, what is the synchronous motor? We know that synchronous motor is the one which runs at synchronous speed. That is the characteristic feature of the synchronous motor. What is that? Synchronous motor, typically abbreviated as SM, runs at constant speed called synchronous speed. Okay. So, and this synchronous speed, what is that? That synchronous speed is actually in terms of revolutions per minute 120 f by p. We know that, where f is the frequency in hertz, and then p is the number of poles. It is the number of poles. We know about this. This is the frequency of the AC supply given to the motor. It is the number of poles for which the winding is done. This is in revolutions per minute, and the synchronous speed as well can be represented in radians per second as 2 pi ns by 60. So the synchronous motor is the one which runs at this speed called as synchronous speed. Now, the synchronous motor itself, the constructional aspects, if we can see, the stator and rotor are the two main parts of the synchronous motor. The stator carries three-phase winding, similar to the three-phase winding of an induction motor, whereas the rotor is provided with poles which are, it is provided with the magnetic poles which are of either permanent magnet or of electromagnet. So the rotor carries the magnetic poles. Those poles can be permanent magnet poles, or they can be electromagnet poles. Okay. So the synchronous motor then has the stator, three-phase winding, rotor, magnetic poles. That's how we can appreciate its construction. Now look at this. The same thing I am putting in a little more elaborate way. Synchronous motor, two parts, stator and then rotor. Stator has three-phase winding corresponding to three-phase supply. We give three-phase supply to the stator, na? Corresponding to that, it is three-phase winding. And the rotor consists of either permanent magnet poles or electromagnet poles. Electromagnet poles are created by having a winding passing a current through that. We know about that, how the electromagnet is realized. In this case, when the rotor consists of electromagnetic poles, I told there is a need for winding and we have to pass the current through that winding, the DC, and this is the rotor. Since we have to pass the current through the winding on the rotor which is rotating, we need slip rings and then brushes. Hope you are catching, because electric contact is to be maintained even when the rotor is rotating. That current is to be passed through this winding even when the rotor is rotating. Are you able to appreciate this? That is the important aspect to be noted. Now, these electromagnetic poles, they can be salient poles or they can be non-salient poles. Salient poles are the ones which are salient, which are visible, which are protruding, which are specific the moment I look at it, I feel, yeah, there is a pole. That is the saliency. It is physically visible. Whereas non-salient poles, pole is there, but not protruding, not projecting. Non-projection is non-salient. Saliency, the physical projection is not there. Protrusion is not there. That is another type. Very interesting. So this is how the whole construction of the synchronous motor can be appreciated. Now look at these figures. It will make our understanding little more clear. This is the stator. Stator has the windings all around, and the stator is supplied with three-phase AC, and the rotor on the shaft is having the poles. Immediately I can feel there are poles, and you can see the winding here. The windings present there immediately indicate what? It is electromagnet, and the poles physically conspicuous by their, can you see this? Conspicuous by their protrusion. This is called saliency, and it is electromagnet. That's why this construction is called salient pole electromagnet rotor. Salient pole salient electromagnetic pole rotor. Saliency, electromagnet, that type of rotor. Now in contrast to that, the electromagnet only, but saliency is not there. Stator is the same, three-phase supply is the same, but when you see the rotor, in this rotor there is saliency, whereas here there is no saliency as such. Protrusion is not there, projection is not there. Instead, the rotor surface is very smooth, circular, and in that we have the conductors, rotor conductors kept at intervals. How many groups like this depends on how many poles we want to have. Here we want to have 4 poles, that is why 4 groups are there. In this group of conductors, the current is coming out. In this group of conductors, current is going in. With the coming out current, with the going in current, there will be flux set up here, which is inwards. Similarly, this group and this group, if you see, the current is going inside, the current is coming outside. Hence, because of these two groups, the flux is inwards, whereas here the flux is outwards. We have concentration of flux, clustering of flux. Clustering of flux is nothing but the pole. That's a very basic definition, very interesting. So we have the poles, and inward pole is south, outward pole is north. Inward pole is south, outward pole is north. What we have ended up with? We have actually realized the poles without the projection being there. This type of realization of pole is non-salient pole construction with electromagnets. Of course, the pole is created because of the current here. Again, the current is to be passed here in this winding, current to be passed through this winding here, whether non-salient or salient. For that we require external source, and connection to this brush and slip ring is required. Okay. Now in contrast, look at this construction. Here also there is stator, same as the above constructions. Three-phase supply is the, but the rotor, look at that. We are having poles, no doubt, they are very visible, but no winding. That means we are having permanent poles, no winding here, no need of slip ring and then brush arrangement. This type of construction is called permanent pole synchronous motor, or that rotor is called permanent pole rotor. So the three construction types, are you clear? Good. So we will proceed. The salient pole synchronous motor, what we saw above, it has the issues of mechanical balancing. Very immediately we should be able to appreciate. When the saliency is the, when it rotates, then if these weights are not properly balanced, then this shaft starts wobbling. Maybe in your two-wheeler, a cycle, or any rotating part for that matter. Typically the two-wheeler, the cycle wheel particularly, if the balancing is not there, then it will give you that effect of wobbling. Na? Here also the same thing happens. And the balancing of these protruding parts is very difficult. That is actually a mechanical challenge, machining challenge. When the parts are protruding, balancing them is a challenge. So perfect balancing is a issue, is a question always. So the salient pole synchronous motor has the problem of mechanical balancing, cannot be very perfect. Hence, its speed cannot be too high, because if we make the speed very high with the balancing not perfect, then the wobbling of the shaft will take place. And if this becomes too much, the shaft itself might physically, mechanically fail. That's very serious. Normally, to avoid that, when the construction is projecting pole type, the speed is not made more. Hope you are catching that. So these motors are characterized by, these machines with salient poles are characterized by low speed. Whereas in contrast, the non-salient pole synchronous motor can be perfectly balanced. See here, this non-salient pole, you have a perfect circle here, nothing is projecting, so machining can be done perfectly. It will not pose a problem like this. Hence the balancing will not become an issue. Since the balancing will not become an issue, it can be done very perfectly. Hence such machines, the synchronous motors, can run at very high speeds. And depending on whether it is the projecting pole, salient pole, or non-salient pole, non-projecting pole, accordingly they are used in the corresponding applications, wherein the applications are characterized by low speed or require high speed operation. Accordingly these constructions are employed. Good. Okay. Next we will look at the working of the synchronous motor. So synchronous motor, you can see the two major parts here. One is the stator, I have shown it as ST. Another is the rotor, I have shown it as RT. The stator is having three-phase winding R, Y, B around the stator core. The rotor is having the poles. Just to make my figure simple, I have shown it as permanent pole. The stator is given three-phase AC supply. Now, the three-phase AC supply is given to this three-phase winding. Three-phase AC supply, we know it is a set of three voltages with a phase difference of 120 degree. Phase, PHAC, phase difference of 120 degrees. Such a supply is given to three-phase winding which is having a spatial displacement of 120 degrees. If you see the angles, this angle is 120, this angle is 120, and this angle is 120. there is a spatial, 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 space, physical, spatial displacement of 120 degrees. This is very interesting. A three-phase AC supply with 120 degree phase difference given to three-phase windings with a spatial displacement of 120 degrees will result in a rotating magnetic field. There will be a rotating magnetic field in the stator, and this field, which is set up in the stator, will start rotating at a speed called as synchronous speed. Sorry. And that synchronous speed, we know it is 120 f by p, 120 f by p, where f is the frequency of supply to the stator, p is the number of poles of the winding for which it is designed. Now, rotating field is the, in this region the rotor is kept, rotor is having the poles, so the rotor poles get locked with this rotating field. These are the poles, there will be magnetic field, it will get locked magnetically with the stator, rotor poles will get locked magnetically with the stator poles, and rotor starts running, rotor also will start running. It is something like this stator field is rotating, this rotor also will get locked with this, and both together will start moving, both together will start moving hand in hand. That is the magnetic lock. And when the rotor starts moving, because of this magnetic locking, rotor also moves at the same speed at which this field is moving. Obviously, rotor also will start moving at a speed ns, the synchronous speed. As long as f and p are constant, f and p are constant, ns is constant, and hence the motor runs at constant speed. That's why we call this motor as constant speed motor. Now, we come to the interesting part. The synchronous motor lacks the starting current, the starting torque. It doesn't have a starting torque. It cannot start on its own. Why? It's mainly because at the beginning, when we give this supply there will be rotating magnetic field. That rotating magnetic field will have N and then S sequentially moving. Now there is N here. If a S comes, it will be attracted by this. Immediately N will come. Then this N will be repelled. Immediately S will come. It will attract it. Immediately N will come. It will repel. That means this N will have attraction and repulsion almost simultaneously, because the poles are moving here. Poles are moving here. And because of that, this N will not have a net force created. Magnetic locking with this will not be possible just at the beginning, when we think of this rotor starting from the rest. Are you able to catch that? That is why the rotor doesn't move at all. The rotor doesn't move at all. We say the motor doesn't have the starting torque. Just at the beginning, stator pole polarities change so fast that the rotor, starting from the rest, will experience both the attraction as well as the repulsion. It will experience both attraction as well as repulsion. This results in net torque becoming zero, and the rotor will not start rotating at all. That's why there is a need for some starting mechanism. We have to have a starting mechanism. And in the case of synchronous motor, there are different starting mechanisms. One is using an additional motor, typically called as pony motor. So we have the synchronous motor with normal three-phase AC supply, and then the shaft of the synchronous motor is coupled to a small motor, which is called pony motor, small motor. What is done in the beginning? the poles on this synchronous motor are not energized. Three-phase supply is given. Rotating magnetic field will be set up. The pony motor is started. It will rotate this rotor because of this mechanical coupling. When the rotor starts rotating, when it picks up the speed, when the speed is nearer to the synchronous speed, suddenly the poles here are created on the rotor. Because the rotor now is moving almost at the same speed of the rotating magnetic field, suddenly these poles will get magnetically locked with this field because they are nearer to each other. The possibility of magnetic locking will be there, and once when that happens, the pony motor is disconnected. This will continue to run as the normal motor, synchronous motor. That means only at the beginning the pony motor is used. This additional motor, it is a small motor. It is only to start, not to take the load. It is coupled to the synchronous motor. Three-phase AC supply is given to the synchronous motor. Rotating magnetic field is created. And here only I will mention rotor poles not there. Rotor poles not there. And the pony motor when started, it brings the rotor speed more, and when that happens, suddenly the magnets are created and the pony motor supply is cut off. Synchronous motor rotor stator is rotated by pony motor, and then pony motor supply is cut off. Before that, we'll put here the rotor poles setup, rotor poles setup. Then the pony motor supply is cut off, and when the synchronous motor rotor speed becomes more, it gets magnetically locked because I have set up the rotor poles. Because of this magnetic locking, the rotor also starts moving at the synchronous speed only. Okay, it is something like you rotate this rotor with external force till the speed becomes nearer to the synchronous speed, and then suddenly cut it off. This set of poles on the rotor you energize, those poles get locked magnetically with the rotating field. Here the pony motor helps only in the beginning to bring the rotor from rest up to a higher speed, and it facilitates the magnetic locking with the stator field. It facilitates the magnetic locking with the stator field. And you can see this particular approach is very simple. That's the advantage of this. It's very simple. However, we require an additional motor. That's a demerit. For one motor operation, we require another motor. Though this motor required is less, nevertheless, it adds to the cost. And another motor means more space required, more weight, and there will be very critical issues, because when the application is something like a mobile application, we will be constrained with the space and weight factors, then it becomes a serious demerit. Hence, this approach is not normally employed. The pony motor approach, very old method, very old method. The other method of starting the synchronous motor is starting it as induction motor. This is very interesting, and this is the one that is employed normally. What is done here? Here, any additional winding is provided on the rotor, similar to the induction motor rotor winding. We have induction motor rotor, na, the winding there, na, something like that. That type of winding is provided on the rotor. Like we have the rotor, na, on this face, we will have the windings similar to the induction motor winding. And three-phase AC supply is given to the stator of the synchronous motor. Rotating magnetic field is created, and because of that additional winding, which is short circuited winding on the rotor, the motor now acts as induction motor. And in the case of induction motor three phase, we know there is starting torque, and hence the rotor starts rotating. And when the rotor speed comes nearer to the synchronous speed, then immediately the supply to the rotor poles is given. Till now the rotor poles are not energized. Now the rotor poles get magnetically locked with stator field, and the rotor continues to run as the synchronous motor running at synchronous speed. This additional winding, what we are mentioning here, it also helps to damp the jerks, the jolts normally encountered in a synchronous motor due to torque pulsations. And this additional winding will help to damp them, snub them. Hence this winding is also called damper winding. It's also called damper winding. It helps for starting purpose. It also helps to damp the oscillations, and this approach using the damper winding has the merits that it is very compact, lightweight, and the cost is also less. But the demerit is rotor construction becomes little more complicated. However, this is the method that is employed with the synchronous motor starting. Okay, so we'll stop there. Next class we'll continue.